This is a production of the Chemical Education Material Study.
Electric interactions are everywhere, and not just at turning on the lights. Your hair gives electrical charges to a comb drawn through it. Your clothes charge a rubber balloon rubbed against them. In fact, all matter is held together by electric charges. This is a very simple electrical generator. At the electrodes, a spark is observed from time to time, indicating the flow of electricity between the terminals. Even when the cranking is stopped, separated electric charges persist. See what happens when a conductor narrows the gap. Here are different electrodes. The generator is started. The spheres move together, indicating attractive forces between them. A battery also generates electricity. We can connect it to electrodes immersed in chemical solutions. Again, motion occurs. Here in time-lapse photography, we can see the movement of the colored substances within the tube, indicating electrical interaction. What is the relationship between the electrical interactions that move the chemicals and the electrical interactions that move the charged spheres? Here we bridge the gap between charged electrodes. The electric interactions disappear. Now we've hung both spheres from the same electrode. The spheres repel one another. Now the spheres are on the other electrode. When the generator starts, the spheres again move apart. Thus, if the spheres are on the same electrode, regardless of which electrode it is, the spheres repel one another. When the spheres are placed on opposite electrodes, the spheres attract one another. We explain these attractions and repulsions by using the electron and proton model of matter. Electrons, represented here by a minus sign, and protons, represented here by a plus sign, are present in all matter. We represent the many billions of electrons and protons contained in one of our spheres with these few symbols. If we add more electrons, the sphere becomes negatively charged. It holds more electrons than protons. If we remove electrons, it becomes positively charged. There are more protons present than electrons. An object which contains an equal number of electrons and protons has no net charge. It is uncharged. When spheres are suspended from opposite electrodes, the generator can remove electrons from one sphere and add them to the other. Attraction occurs. The left sphere now has a positive charge and the right a negative charge. The attractive force between the unlike charges causes the spheres to move together. How can this force be measured? Here is an apparatus which will allow us to measure the force acting on a charged object. A chargeable sphere is suspended by a non-conducting nylon thread from a sensitive balance. Turning the left knob releases the balance and illuminates the fractional gram scale. The reading of the balance due to the force of gravity is 11 grams, indicated at the left, plus 0.130 grams, indicated on the fractional scale. The total reading is 11.130 grams. Remember, 11.130 grams. A second sphere is supported by this non-conducting plastic rod. Now we charge the two spheres oppositely, one negative, the other positive. Opposite charges should attract. The reading on the left again is 11 grams. The fractional scale now reads 0.493 grams. The total is 11.493 grams, which is considerably more than the 11.130 for the uncharged spheres. What does this increase represent? The force of gravity causes the original reading on the balance. Then, with oppositely charged spheres, the balance reading increases by an amount due to the electric force. If we subtract the grams due to gravity from the total grams with charge present, we get a measure of the electric force. When the lower sphere is brought closer, the gram reading increases and then diminishes as we move the lower sphere away. Electric force and distance are interrelated. Let's measure the force at various distances. Each of these blocks is 5 centimeters thick. By removing them one at a time, we can change the distance between the spheres. The spheres initially are placed 10 centimeters apart. Now we make sure the spheres are fully charged. The balance now reads 0.671 grams on the fractional scale, or a total of 11.671 grams, which is much higher than the 11.130 reading for the uncharged spheres. We'll record the reading for each distance between the spheres. At 10 centimeters, 11.671 grams. Now, by removing one block, we increase the distance between the spheres to 15 centimeters. The reading decreases with the spheres farther apart to 11.364 grams. Increasing the separation to 20 centimeters gives a balance reading 11.263 grams. Finally, let's separate the spheres by 30 centimeters. The balance reads 11.187 grams. Let's remove the lower sphere completely. With the lower sphere a large distance away, the reading is 11.128 grams. The same with an experimental uncertainty as when we started with an uncharged sphere. Subtracting the reading due to gravity from the reading at 10 centimeters gives us 0.541 grams for the electric force. In a similar manner, the electric force for each of the other distances is calculated. At a very large distance, the electric force is so small that for our purposes we can consider there is none. When these values for the electric force at each distance are plotted, they give a smooth curve. Data for other distances would give additional points lying on the curve. As the distance of separation between charges increases, the force decreases. The equation for a curve of this type is F times r squared equals k, a constant. F is the electric force. R is the distance between the centers of the spheres. F times r squared should give a constant product. Let's check this out. For the first measurement, 0.541 grams times 10 squared is about 54. In a similar manner, we can calculate the values for the other distances. The results show that the product of force times distance squared is constant within experimental uncertainty. This relationship, F times r squared equals k, applies to the interaction of oppositely charged spheres. It is also found to apply to the interaction of like charges. Thus far, we have seen that uncharged, that is, electrically neutral objects, exert no force. Opposite charges attract, and like charges repel. The force of interaction between two charged objects varies with the distance between them. Let's apply these ideas to chemical behavior. Many solutions, such as these, have similarities in names. There are many potassium compounds and many sulfates. Because all the other sulfates seen are colorless, we assume this blue color is associated with copper. Is the blue copper electrically charged or neutral? Let's see what happens when we place aqueous copper sulfate in a glass tube between two chargeable electrodes. The solution is poured in the space between two plugs of white gelatin-like material. The gel separates the solution from each electrode. The gel can conduct an electric current, but does not allow liquid to flow through it easily. The battery will remove electrons from this end, making the electrode positive. And will supply them to this end, making the electrode negative. When the battery is connected, the electric interactions begin. Time-lapse photography compresses 2 hours of actual time into 15 seconds. There is a large movement of the blue color to the right, toward the negatively charged electrode. The blue color must be due to positive ions of copper. How big is M? Let's repeat the experiment with potassium chromate. Since aqueous potassium ions are colorless and chromate solutions are yellow, we believe the yellow color is due to chromates. We'll pour the solution into the center section of another tube, arranged as in the previous experiment. This time, repeating the time-lapse photography, we again see motion. But the color moves toward the positive electrode. The chromates, which from analysis have the formula CrO4, must be negatively charged ions. How big is N? Now the apparatus has been modified so that the solution containing positively charged copper ions is placed around the positive electrode. The solution containing negatively charged chromate ions is placed around the negative electrode. The battery charges the electrodes, and as you would expect, the colored ions move through the gel in opposite directions, consistent with their opposite charges. But there's a new effect. A brown region develops. Let's disconnect the battery. The central brownish region suggests that a new chemical substance has been formed where the copper ions and the chromate ions meet. What is this new substance? If we simply mix the original solutions, will this same brown substance form? Yes. Apparently the gel and the electric current are not required. Copper chromate forms when copper ions and chromate ions come together. Analysis gives CuCrO4 as the formula. One copper has combined with one chromate, so the ionic charges must be the same. Analysis shows 2 plus and 2 minus as the charges. To understand the precipitation of CuCrO4, keep in mind our previous equation. F times R squared equals K. Remember that the positive copper ions and negative chromate ions not only move in opposite directions between the electrodes, but as the distance r between these ions decreases to atomic dimensions, the force F between the ions themselves must become large. Instead of passing one another, most of these oppositely charged ions attract one another, adhere, and form copper chromate, which has no net charge. CuCrO4 precipitates. Electric forces hold the solid together. Both the formation of the precipitate and the directional movements between charged electrodes are consistent with the presence of positively charged copper ions and negatively charged chromate ions. All electric interactions in chemistry may be interpreted in terms of these two kinds of electric charges, which we call positive and negative. Knowledge of electric interactions not only helps explain the movement of ions and the formation of precipitates, but also the formation and behavior of all chemical compounds.